Okay, I'll talk about way to determine the weight. Here is the overview, um, and so the weight determination in the neural net is pretty much the core of every neural net. Once you got that down, you pretty much I think with my limited understanding, you understand all the neural net, but just basic the basic, and then the rest is just the advanced like the structure of different neural net. The way it itself is pretty much the at core in my mind is just try to understand how it just at core itself is try to determine the weight and bias. So here is the steps of calculating it. So first you have an input and an output within it. Those are just like a hidden layers of nodes, and then for between each layers you have weight function and bias. So you initiate the weight and bias, the first step, and then you propagate through different layers. So from the first layer to the first layer, which means input layer. This is pretty much input, and then propagate to next, and then you got from this the initiative like weight and bias, and this is the activation function. Um, then you got this second layer of uh, all the neurons in the second layers, and then you put the second layer to the next layer, and then propagate so on and so forth until you get the final layers. Then you calculate the cost function j, and then you the pretty much the cost function is determined by the loss function, and the average over the number example. M is the number of example, where A is the given layer of nodes of layers, and the y is the output, the expected output. And then after that, you determine the weight and the bias by doing a gradient descent. The gradient descent you can understood as like if you have a hill, if you stay here, and you want it to come here, then you just want to calculate the gradient, and then go to that direction. So you imagine you're on the hill, you just want to see the gradient and fall, and then fall. So depends on how fast you fall, where the speed of falling pretty much is the learning rate alpha. And then eventually you will be like, imagine you will be like this, and then eventually goes to really close to the local this minimum. So after that, you updated the weight and bias. Then you repeat, you updated that pretty much a back propagation, and then you go back to this propagation, and then do it all over again, and rinse and repeat until you got a desired parameter match. Like for instance, cost function low enough, you get the weight and bias. So it's all theoretical. Let's use a very simple example. Let's try to use a two-layer neural net to fit a y equals to y equals 2x. So let's just set up like 10 different 10 different numbers from 1 to 10, and then since y equals 2x, then it's 2, 4, and then to 20. We set the loss function as a mean square error, and then for our case is let's just make the activation function a linear function. First, we initiate w equals 1 and bias equals 0. Then we propagate since to the next node. the W equals to 1 and B equal to 0 and G equal to 1 since it's linear. Since A1 is pretty much an input, then it's pretty much just A2 equal to A1, then we got this. We're going to calculate the cost function. Since this is going to be pretty high, let's not spend too much time calculating it. I have an article in Medium. I think you can read it if you want to. So we can update the weight function, and we first calculate the derivative dj over a partial j over a partial w. Use the chain rule. We just pretty much do the, imagine this is squared, then we get this as a, then we got 2a minus y dad dw. The chain rule is, so d a minus y d square minus dA minus y d a minus y dw. Since y is a constant, this thing become 2a minus y, and this become dA over partial a over partial y, and that's what we have, because there's a 2 there, so it just cancels out. Then we have alpha m a minus y dA dw. Since a from the previous expression, propagation expression, we have this. We plug it back in here. Then we have this. Since those is not a function of w, then we left with this become, this should be j. And then we pretty much, this is a dot function. We calculate this, so a minus y, which is 1 to 10, 1 to 10, negative 1 to 10 to 1 to 10. Then we have negative 385, and there's a minus sign, and the sample size is 10. Then we have w plus 385 alpha. And let's imagine the learning rate alpha is 0.01, and then we have omega, the w equals 1.385. Similarly, we can do the updated b in the similar manner. Let's not go through the detail too much, because yeah, this is correct. A2 equals this, and then we plug it back in. Since we only have this, so this is only have this, then the derivative of this become 1. So we're left with this, and given alpha equals 1%, and then we have 0.001, and then that's the updated w and b. Then this become the new w and b. We repeat this iteration of those steps, and until we got pretty close to w equals to 2, b equals to 0. And here is a plot. We starting from here, and then slowly go up until we go matching pretty good with the data. The data is a red dot, and the solid blue line is the final one, which set criterion J as 0, 0, 1. If it's less than 0, 0, 1, then we stop. So let's look at the code. So that's in Python. We first initiate the x and y equals 2x, and we set the learning rate 0.1 and criterion for j as 0.01. Here is a definition of cost function is mean squared error. This, and we do the step 1. We do the step 1, initiate W and B, and we give a linear activation function, and this is just the putting the first entry of the list, and J just give it a very large numbers to go through the first steps, pretty much. And now is a step that has a need to be in the loop, because we're gonna repeat those 3 steps until we get a desired small enough cost function. Step 1 is propagate. We'll propagate to the next node, and then we calculate the cost function to see if it matches matching the criterion, and then we calculate the gradient. So this is a partial J, partial W, which we have found here is a2 minus yx. This a1 is x pretty much, and sorry, this is correct. This is a2, and db similarly we calculated before. Here is a2 minus y, and this update pretty much a dw is a negative alpha dj dw, same thing for db, and then update a w and b, and then add that to it, and rinse and repeat until we get the desired j. And I just, for the plot purpose, I added 0 to the plot, and I made it like a light blue or semi-transparent blue lines as a progression towards the final one, and this is the final one chosen the last in this last element of the W list and B list, and I print that out as well. And then the all the red dots are the final results. Are the data points. And yeah, that's it. So we can simply run this. This should be run in pretty fast. And there you go. You see from the initial x equals y, which w equal to 1, all the way up to the final results. And here is just to sanity check this. We calculated by hand. Remember, we calculated by hand here. W equals 1.385, and we got 1.385 here. B 0.05, 0.05, and then we keep going to a better and better fit, and finally get to the result that we desire. I mean, this is the J is set up pretty loose so that it can run in a short time. You can run for more iterations, therefore got a better fit. And this is pretty much the core concept in my mind of neural net. You just pretty much find the best weight and bias for each neurons for different activation function, different loss function, and different learning rate, or different learning rate changing mechanism, like Adam and other type of learning rate changing mechanism, and also you can have different structure. You can have convolutional neural net, regressional neural net, so on and so forth. But in its core, in my mind, so far as I understand, is just pretty much solving this. And I will link the better written note on the description.